remind you, right? We have to go from the morning that John has done a very good job motivating in many of the from scientific engineering or the natural high dimensional data has a very important things are very low dimensional structures, and it connects to some classical theory, right? How do we, in a very in a nutshell, in a very idealistic model, try to solve inverse problem from the measurements to recover those low dimensional structures, right? The classical theory from compressive sensing, from signal processing, and actually capture the essence of that. But those theory has been very much at the very foundation, the core of all the problem we're dealing with. But it is making, because of that, but actually making it very simplified. Idealistic assumption is that the structure of the data is already linear, right? Either it's k-sparse, piecewise linear, or it's low rank. Right? And also that even in those cases, the problem that the structure of the data is linear, but the meaning of this problem, try to solve those inverse problem, the formulation could still be non-convex. That's Yu Qian, the second lecture, has talked about it. Progressively, like in the case of Sam and also in the case of Zihui, we just heard, is that the very fundamental role, right? Why this empirical success of deep neural networks in the past 10 years, right? In many of the practical data, like images, natural languages, or speech, and so on, it's actually precisely one of the messages we're trying to convey is that still, very importantly, they try to capture the low dimensional structure of the data. Nevertheless, the data may have nonlinearity, right? They're no longer as simple as idealistic as piecewise linear or piecewise or like a low rank or sparse signals. So this is something that we try to put together, right? In the past 10 years, we've seen tremendous empirical and inductive approach to practice gazillions of variants of neural networks. Many tricks, many phenomena, many understanding, right? Including the Sam's work, and also Zihui has talked about different aspects of either the network architecture from statistics point of view, from optimization point of view. I've seen. So the question is, maybe it's time, right, after 10 years, after we have seen all these pieces, maybe it's time we probably have to do a little bit of integration, try to understand things from more deductive perspective, right? Can we have a full sort of framework, try to unify all this, integrate all the observations, provide a unified assumption, a unified explanation to all this. So this is kind of the effort we, my research group, and also with the colleagues, John, and also many colleagues here have been embarking on in the past few years, right? They were trying to present some of our discoveries, try to connect again some of the historical pieces, views, and also try to integrate under a more unified framework. So how do I go back? Sorry. Yeah, this is kind of, we're trying to give a little bit precursor, some of the motivations. I think one of the things this tutorial, probably different from others, we try to really try to understand what is the right problem we're trying to study, right? I know it's a mouthful, it's actually mindful, right? There's a very intense messages. It actually connects to many subfields. And also there's like hundreds of pages of books probably have to digest. But hopefully, we try to give you the right motivation so that you know what are the right question to ask, what problems, right way to think about those problems, right? Then you know the doors to the right approach to this problem. So I'll give a little bit of precursor. I'll give you a little bit of examples of why motivate us, and maybe it's useful for you to understand, right? And then we'll try to make an attempt, can we actually unify things from a very deductive point of view, right? Making very simple assumptions, very unifying assumptions, so that we can maybe we can derive everything from scratch, right? Show the power of deduction. And not only just make the objective clear, but also make the network architecture clear, right? Everything becomes transparent. Is that possible? I mean, not just the object function, the architecture, each layer, even every single parameter, right? Leave no stone unturned, right? So that's actually, can we do that? And also the most important thing, right? Many things, were frustrating with theory the past 10 years. Yeah, maybe you can explain a little bit of things, right? chasing practitioners' tails, I would call that, right? I mean, we can explain, oh, this is what they do, this maybe this trick's the reason why it works. But somehow, can we impact practice? Can we say what they have done not good enough, right? Go way beyond what they can even imagine with the practice. So that's where we're going with a good. If we have a good theory, we should be able to do that. So let's just start with some motivating examples, right? That what motivated me to connect, to look into like John, and we started looking at why there's a connection between neural networks and sparsity or low dimensionality, right? We didn't start it. Actually, Yang Kuhn started it, right? Before the neural network, deep network was even popular at all, right? So we all know, right? This algorithm, John has talked about a lot, right? We try to solve a sparse solving y equal to ax. This is a very simple problem. X is sparse. I mean, the algorithm to solve this is a classical algorithm, right? Solving the lasso problem. And the algorithm solving this is actually very simple, right? Take the gradient descent and take the iteration. This is gradient, and we do soft thresholding to find a sparse solution. And this is algorithm. This is a way predate neural network, right? But if you look at what this algorithm is doing, each step take a gradient, which is a linear operator, right? And then do a soft thresholding. And look at the function, right? The software function. And now if you compare this to modern neural network, this is exactly the kind of meta structure neural network has. Linear operator plus some nonlinear thresholding. It even looks like, right? And there's no surprise. This is the work around 2010, before neural networks, right? This Yang Kuhn already recognized there's a similarity to the algorithm to pursue sparse solution. Just looks just like a neural network, right? Then, of course, the algorithm actually unrolls it to just do the gradient descent, right? It said that if I just fix number of iterations, maybe the gradient descent may be not good enough. What I can do is that I can actually change the parameter per layer, making those here. Sorry, oh shoot, I'm speaking in the wrong direction, right? So here, the linear operator, each layer is already fixed by the known dictionary. But what if it's not good enough? I can fine tune it. Nobody can stop me from doing it using backpropagation, right? I just fine tune them with a little bit. That makes the algorithm solving the sparse solution much, much better, it turns out, right? So in fact, he actually interpreted this, the algorithm, classical algorithm to solve sparse solution as a neural network. Right? We're going to do the opposite. Right. Another example actually motivated me is that, remember, this has been a recurring problem, right? We try to find a transformation. This is the holy grail for signal processing problem, right? We have some many data. Why? We try to write down a transformation equal to AX. Here, I consider A is the orthogonal transformation. I ignore the A transpose, just to be consistent with my notation, right? So basically, A is a square matrix, then the Y is equal to A transpose X. It's similar to the problem we're dealing with in the morning, just notation-wise. So the point is that the whole holy grail of signal processing is always trying to find a transformation such that the structure in the data, observed the data Y, revealed itself, right? Become very sparse, become very low dimensional, right? So you can think about this classic example. A is just a Fourier transform. If I have a audios, low bandwidth, right? The band limited signal to a Fourier transform. Wavelets, A could be wavelets, right? So another question is about, of course, in the data-driven approach is what if I don't know the analytic transformation? I wanted to learn from the data. I want to find among all transformations, all orthogonal transformations, which one gave me the most sparse solution, right? This is now. Interesting thing is that right today, I mean the Yu Qian and also that Zihui has talked about this. There's a nonlinear formulation to this problem. And turns out there's actually a very interesting dual problem, right? We were trying to make the x zero, the zero norm of x small possible. Of course, you can replace zero norm with a one norm, right? But regardless, this still is a binary problem. It's still a non-convex problem. Even if you replace this, convexify this object function. Turns out, since you are dealing with a non-convex problem anyway, you don't have to, solve on just using one norm. Turns out, if you restrict all the features on the sphere, right? So minimize the zero norm is actually equivalent to maximize the four norm. Right? So you can think about the four norm is kind of dual to, but it's maximizing the four norm, minimize the zero norm. This is kind of interesting with geometry. Now, so if you do that, if you just say try to maximize the four norm on the sphere to look for the optimal the diction transformation, that also will sparsify this. So if you do this, if you take the gradient descent, just do very simple gradient descent on this, right? I hope we sold you the idea, right? If you have a long convex optimization, don't be afraid of just using gradient descent. Actually, something magics will happen. In these cases, it actually works very, very well. This gives you some of the most effective, still probably by far the most effective. Just do the gradient descent on this, right? And yet, this simple gradient descent algorithm actually has a very interesting interpretation, right? It's actually trying to apply every iteration. It's just apply the orthogonal transformation on the data. Remember, just computing. If you're computing that increment, every gradient descent, you just apply the little bit of rotating your data, so to find and make the data more and more sparse, right? So you naturally get a deep network. It's actually concatenation. Each operator, each layer, each iteration only depends on the feature already transformed. Has nothing to do with the original data, right? It already gave you from the original observed Y. You just apply a sequence of orthogonal transformation. Eventually, it will give you the optimal transformation, optimal representation. Right? And if you look at the way to compute each layer, each delta R, it's exactly a linear transformation plus a nonlinear threshold, right? And in fact, this is not unique. This is not the special. Turns out this is exactly corresponds to how people computing using power iteration to computing eigenvalues, eigenvectors, and also how people use this to compute ICA, right? This is a fast ICA is proposed by the guy called Abel Havanari. The guy actually proposed the score function for diffusion models. Right, it's the same guy. Actually, he did the score matching function precisely to compute ICA and for dictionary, not for denoising, because that's too simple. Right? This is actually much more important problem to do. What I'm trying to say is that this is a sort of give you a little idea, right? Seeking the sparse representation is exactly the idea, the reason why we see deep networks, why we see the kind of structures. This is another work we did a long time ago, right? We call it PCA net, right? So there's a lot of learning we try to do. We build a neural network, we do backpropagation to tune it, right? Fine, if you have a lot of GPUs, but turns out we should understand what really each layer is doing. Can we ask that question? What each layer is making things better or worse? Right? This is my first attempt to neural networks, right? At that time, everybody is saying, "Oh, we want deeper, bigger, wider." Right? So at that time, we asked the question, then can we justify that? Right? Can we do a simplest deep learning baseline for image classification? Right? And we build, but what about we just do the simple PCA? Each layer just do patch, image patch, do a PCA. Learn the filter, convolution filter. Build this in the most simple way. Everything's feed forward, absolutely no backpropagation. The network doesn't even know what the task is. Okay, just do PCA for the inputs. Build the filter, right? And each layer is actually the nonlinear threshold in just the binary. This is the simplest network you can imagine, right? 2 layers, 3 layers. By the way, you can even replace each layer, the PCA filter, with a random filter. We call it a random network. This is 2013 or 14. And the surprise thing is that this actually gave you a state of art at that time on all the face image datasets. Of course, we couldn't publish this paper for 2 years. Why? It gets rejected because people think deep network is everything, right? The simple network like this, why should it work? No. So eventually we published it in the journal. And we'll loop back to this, right? So this is actually ancestor to something quite remarkable. By the way, you can actually replace all the filter with completely random filters. you only draw percentage by 1 or 2%. Right? There's something very, very interesting going on. Now, transformers, right? So Sam also Zihui also mentioned, right? Transformer. What transformer is doing? Very simple. Some attention head, and then with some residual block, and this is attention head. It's computing the autocorrelation, right? You can see that if you see the layers from early layers, the representation is kind of dense, but eventually actually becomes very column sparse. That's another feature. It sort out the features, try to make it linearize those features. Right? This is empirical observations. It does something very interesting. Try to organize the data in some way. Right? We'll see why this shows up in a second. So all these pieces, different things, like you are solving a big jigsaw puzzle. So what is really trying to do, right? You see, right? So then can we just do things from a very deductive way, right? If we do that, right, those are the two pillars of modern science. One is inductive, one is deductive, right? We've been doing that for thousands of years, but they actually help each other, right? So for example, we want to derive everything from scratch. So can we just agree on the minimal set of assumptions? We're dealing with many, many classes of data. Let's imagine ImageNet, right? Thousands of classes, objects. Then each class may have some structure, right? Apple, orange, a set of images. You can gazillions of images of an apple, but they must be similar to each other, right? They lie on some very low dimensional structures. Imagine each image is a million dimension, minimum pixel, but the set of apples maybe lies on some, in that million dimension space, this is just some 5 or 6 dimension manifold, nonlinear manifolds, like maybe not a 1 dimension, but maybe some fixed number of dimensions. And also, we are making assumption that the apple and orange can be separated, just like Sam also illustrated with the model problem with 2 curves, right? They should be separable, right? But of course, in the real data, maybe the dimension is not a 1, but a multiple, and then but they are separable also. Right? You may not know how, but they are separable. That's why we can tell apple from oranges. Now the question is, what do we try to learn? Ask you is a very simple question. Fit label, things, generated model. Think about it, right? So our memory is trying to remember, right? What do we try to learn? Doesn't matter a machine or an animal or a human, right? Maybe we can agree on is that maybe we try to sort things out, right? Doesn't matter we do this for classification, for generation. Our memory, we try to find some kind of very compact and structured representation of the data. In fact, that's what the deep network started with, right? We try to map all the blue curve, for example, right? All the points on the blue curve to something like one hot, like we just talked about, right? This collapse into this one singleton neural collapse, right? And also, how do we do this? You try to optimize the cross entropy measure, right? Make sure the output of some network, of course, this is a very complicated map. We already know for many, many years, people don't know how to build this map. But of course, neural network says, well, let's try some neural networks, right? Then we can train this, make sure, enforce the network output match with the one hot label. Right? Again, this is a way to seek to transform the data so that the data has structure, right? Force the data to fit this kind of structure, simple structures, compact, very simple structures. Of course, Zihui has illustrated this very well, but this, eventually leads to neural collapse with good or bad things. We'll see that. But there's some elephant in the room, right? As Zihui says that if we choose a network too complicated, these guys can fit anything. You can, randomly shuffle the data, randomly shuffle the label. You can fit everything, right? And it's actually not, just as Sam also mentioned, it's not actually even guaranteed to be robust or even invariant to transformation or deformations. There's a lot of things we strap under the rug, right? For 10 years we have headlines how wonderful they are, but actually a lot of bad things gets ignored, acknowledged, especially for understanding. Right? We sort of cherry pick the results without guarantee that. The question is, I probably couldn't care less. Is actually I care more is about what the network actually, what the machine has really learned. Right? Can we explain that? Just be able to fit the label. It doesn't say anything about the data, right? Because the label can be arbitrarily assigned. The network still can fit it. So what the network is trying to do. So there has been some existing theory trying to explain, right? So maybe, and this is the information bottleneck came out early on, is trying to say, oh, but maybe then what the feature mapping F is trying to do is try to extract some features that really match the label you care about. Well, if the label is what you care about, this may be the right thing to do, right? You wanted to find out the feature that is in terms of information, right? The mutual information between the feature and the label are maximized. And you throw away in the data whichever is irrelevant to the label, right? You minimize the mutual information between minus the mutual information to XMC. Right? This actually was celebrated as one of the ways to explain deep network, what the deep network is doing. But in my view, this is exactly the wrong way. Why? Do we care about the label or do we care about data? If you care about label, great. That's what we care about data. What do we learn is X, right? We want to understand what the X is. Right? So this may be able to explain a little bit about what classification is doing, but it's definitely not helping me to understand what I have learned from the data. Okay? The label can be arbitrary. But actually, there's a bigger elephant in the room. It's not just a formulation, not just what you want to do. What is the question? What can you do? Right? It's a computation. You can, of course, you can write down, oh, this may be something I'm optimizing the mutual information and between labels and this. The question is, can I compute this? If this is something I'm doing, must be able to evaluate it in terms of this thing, right? Turns out that when you're dealing with data in a very high dimensional spaces, especially those distributions are degenerate, those almost all the entity, right? You saw very popularly almost every NIRPS paper start with, let's talk about entropy, let's talk about mutual information, let's talk about Kell divergence, Jensen-Shannon distances, right? And the maximum likelihood even. None of them is even well defined. Let alone, even they are well defined, most of the quantities are intractable to compute. Right? Then you should ask yourself what the heck you're doing. All right, computationally. If you cannot evaluate those things. Of course, why there are 10,000 papers? Everybody approximate. Propose different way to approximate. Sample, lower bounds, different surrogates, right? Everybody claiming my approximation is better than yours. See, it works better on those examples. Right? Keep doing that. Right? We're just pretending we're making progresses. Right? We're not. Not conceptually, not computationally. Right? So this is actually questions that if you write down all those comparative concepts, you cannot even evaluate them, right? It's hopeless to compute them accurately. Then can you guarantee anything at all? Especially computationally, you cannot. By the way, this is not the old problem. This is not a new problem. This is exactly the problem. Renee, he's not here, probably jet-lagged, right? Renee and we went through about 15 years ago when we were doing image segmentation classification, right? Because even you assume your data lies on the subspace, even it's linear, let alone it's non-linear, right? Even on linear subspaces, right? You cannot avoid those problems. Right? Almost all the classical information theoretical statistics formulation, they become degenerate or ill-posed. Then computationally, none of them work. Right? So we actually struggle with it. We actually wrote a book about the generalized PCA on the whole subject. It took us about 10 years to sort things out a little bit. Right? We tried everything. Right? Fine. For example, how to do clustering. For example, we assume our data lies on multiple classes, right? Each one on some subspace. I'm not even talking about manifolds. Think about even simple case, subspaces, right? Well, everybody's very, very, arrogant. It's very simple. How do we do clustering? How do we classification? How do we do clustering? Well, you model your data. This is multi-class. You model as some mixture of distributions. Write this down. You run EM algorithm, right? By the way, in 1990s, that's what the Hinton works on. Okay. Everybody write that. This is statistical 101, right? If you take a statistical courses, the people teach you how to do this, right? But if you're dealing with high dimensional data, like images or text, speech, right? This is not defined. If the support of the distribution is singular, And why are you doing this then? If it's not even defined, you cannot even evaluate. Even this is defined, even if it's Gaussian. Evaluating this, sampling high-dimensional Gaussian is a nightmare, by the way, right? So why are we doing this? So at that time, we actually really struggle with this. We cannot even segment images, right? We cannot do the empirical. Of course, you can approximate. Of course, you can do empirical things. You can hack, right? That's what people do. But then the question is, can we do this in a slightly more formulated way, right? More formal way. So that's one thing we actually realized, that maybe you have to deal with this degeneracy of the distribution in a more principled way. Let's actually come up with ideas that maybe, why do we cluster data? We start asking ourselves some very annoying questions. Why the heck do you want to cluster your data? You must gain something, right? So, and one thing, how do you measure that gain? Right? Turns out this actually traces back to the very fundamental problem question like Shannon has asked, right? In the information theory, how do you measure information? How do you evaluate things, right? So this is something we actually realize that. So if data has this kind of no-dimensional structure, has this kind of structures, right? So something, you gain something by looking at, if there are two components, x and y, right? By looking at this, if you can separate them correctly, you must gain something. How do you measure that gain? Hence, one way to do that is very, very simple. If I don't separate them, to code them as one distribution, I find out how many bits I need to do that, to specify the location of each point in that space, in the whole space, right? Then I need to code the whole volume of that space. If I can separate them properly, then each one, I only can code those with different set of volume. The volume becomes small. So the notion of compression is behind everything, right? The reason I separate things because they compress, I get a much more compact representation. Very simple like that. Hence, the difference between the whole and the parts, the volume of the whole and the volume of the parts, that's exactly called the information gain, right? And so then this will become very simple, right? I only have to evaluate the volume of the whole minus the parts, right? If the parts volume is less than the whole, I'm done. I separate them. If smaller, I don't do anything. Right? Now the question becomes, how do you evaluate the volume of a distribution of some data in high-dimensional spaces? Right? Turns out that's a very hard problem. Right? Although you can write down rate distortion and so on and so forth, but it turns out that computing those things is NP hard in general. But we're lucky only in one very special case, is when your data lies on the distribution, if your data are Gaussians or subspaces. Turns out there's closed form formula to compute the volume. Right? So how do you, the basic idea, actually this is from Shannon, right? How do you evaluate the volume of some spaces? Then you just give me let's say a size of the ball, beans, or just pour that into that volume. Then you count how many beans in there. Right? That's almost a universal way to evaluate the volume. Right? Of course, you have to specify more accurately, you give a smaller bean. Right? If you don't care, you get a bigger ball. Right? So you pour into that space, so you count how many balls there. The sphere packing, basically. Right? And turns out in the case of Gaussian and subspaces, magically, it's the same formula. Right? And so you can derive this formula purely algebraically or purely statistically. There's the same formula, which is very, very accurate. Right? We'll see. I mean, this is something, right? So this is just a log determinant. It's actually the volume, how many balls you pack there. It's a very interesting log determinant of this regularized covariance matrix, right? Turns out everything comes from here. Residual network, transformer, all comes from here. Okay, we'll see that in a second. Right, so now, once you can measure the volume, the whole and parts, then it's easy, right? All I do just compare, right? So if I the data like this, if I split them in this way, proper way, the parts, sum of the parts is smaller than the whole. Of course, there's some overhead to code the membership if you want to do the Huffman code, right? And then how do you do this? This actually turns out to be a very interesting algorithm. And once this just tells you, once you split the data, it can tell us if you should split it or not split it. But how to split it still doesn't solve that problem, right? There's combinatorial many ways to split the data, right? You have to try all of them. Turns out this measure is very accurate. It's a log determinant measuring the volume. And actually, you can start from the bottom, right? You don't have to tell where to split the data. You actually, there's any 2 points. You merge them if they can save bits. You start from grassroots. Right? So it actually gives a very simple merge data. You merge data until any merging will not result in reduced number of bits. Right? So this actually works magically. Right? It's still the best, probably arguably the best clustering algorithm. Far better than k-mean, far better than any other factor method. Right? In our book, we can characterize. It actually has a very interesting phase transition behaviors. Right? I'll skip that. But before deep network, this gives the state of art unsupervised image segmentation algorithm. Everybody know what happened to deep networks, right? Everybody started to supervise image segmentation. Right? But this is still the state of art with unsupervised. It's completely unsupervised. Don't need any training data. Just merge similar data points together. Right? Then this is purely unsupervised. We actually started with unsupervised problem. Then of course you think about what do I do supervised? If I do have data, right? Apple, orange, there's a new data comes in. Is this apple or orange? Right? It's a classification problem. Then how do we do that? Again, very simple idea is that ask yourself, then you must gain something by assigning the image looks like apple to apple, right? Then this is actually, again, is a compression problem that you can actually see that whichever cluster takes minimal number of bits, extra bits to put that points into it. The minimal incremental volume to claim that points becomes the assigned, right? So that actually turns out very interesting. That we call this minimal incrementation. Just measure the volume together and subtract. Whichever one the delta increase of the volume is smallest, you assign to that. Right? And it's all really has a minimalistic flavor to this, right? Everything is about compression. Everything is about the most compact representation, right? Measured by bits, measured by the number of balls, right? Nothing else. Everything is a counting game. Turns out this simple counting bits assignment actually converge to, if you have data size goes to asymptotically goes to infinity, this give you precisely map estimation. Actually does exactly theoretically the right thing, right? It's very simple bin counting bits. This is our, and it has some very interesting behavior. This is our NIPS paper around 2009, I believe, right? So you can see this is the first paper, very first classifier actually extrapolate structures. Right? This is what the nearest neighbor will do. This is what the nearest neighbor will do. This is what the SVM will do. Right? This one you can see never has seen any sample on the left, but you will see this. I see a line. This actually can extend to the other side of the data. Completely give you a classifier, actually respect the low dimension structures. Right? It does that automatically. At that time, we were pretty happy, right? We actually see this actually does the right thing theoretically, and also really unifying the notion of compression seems to unify in a supervised, unsupervised fashion, right? Everything's reduced to data compression. Of course, although we only was able to work for the case of linear substructure and the Gaussians, mixture of Gaussians, right? But we're happy. But there's one thing problem with this is that we'll see that this is actually only dealing with Gaussian or subspaces, right? But we just said the data could be nonlinear, right? Then the measure is off, right? If my distribution is curved, right? It's not a subspace, what do I do? So we stop there, but then neural network become very popular. Then we start to re-examine neural network. We started, this is our method of compression, only the measure. Remember, we can measure those rate distortion or coding length only when the distribution is linear or Gaussian. Right? Other distribution is very hard to compute. Okay? You can write down IXY, mutual information. You can write down rate distortion function, but you can never evaluate it. Okay? You can talk about them, but you can never get access of them. Okay? Stop talking about them. Okay? If you cannot compute. Everything you put on the paper, there's a price tag. Right? So the question, then we would start to realize that since Gaussians or subspaces are only ones, the distribution we can measure, maybe we can make them. Maybe that's exactly the role of deep network. Right? Our original data distribution may be nonlinear or arbitrary, but the process of learning is precise to make your distribution to some standard structure. Right? So if X could be multiple manifolds, then we can learn the mapping F to make them linear. If this is a 5-dimensional, make this 5-dimensional. If this is 6-dimensional, make this 6-dimensional. And we sort them out. And if those two manifolds are barely separable, we make them orthogonal, just like the neural collapse. Different cluster means are orthogonal. Right? Hence, we call this, right? So hence, the mapping has to do multiple things, right? We try to represent the data, right? Linearize if each manifold is not linear. We compress, right? From a high dimensional sample space to compress. If this is a million subspace, but the minimum of dimension, this could be just a few hundred. Sparsity from separable. But if once this are orthogonal, the representation automatically becomes sparse, right? That's the emergence of sparsity, right? And also we want one problem I'll talk about on Thursday morning, right? We want this mapping not just reduce dimension, or we don't want this 5-dimensional apples all collapse to 1 dimension. Why? I want to know why apple is different from orange. All the characteristics, right? I just don't give me a label. This is apple. Don't tell me why, right? It's collapsed to the one label. That's very bad, right? Tell me the color, the shape, the texture, right? Don't forget that some apple are called computers, okay? Or what if I want to regenerate the data? So I want this mapping to be almost 1-1 so that I can go back, right? For generative purposes. We want to unify everything, right? So the question is, that's something I'll talk about on Thursday. But today I'll focus on the one direction, right? So we try to learn mapping such that make the data one-dimensional linear and also different classes incoherent, orthogonal, and also that hopefully that each class we want to preserve as information as possible, preserving the dimension. Can we do that? No collapse. Again, how do we do this, right? Remember that how do we measure to make this more compact? Oh, I have to measure how good the features are, right? You have to put the goodness of the feature. Again, we know when the feature, if they're linear, we know how to measure them. The volume and the dimension, right? This is the formula. We know that. This is for the whole data set, right? That's why this depends on the number of samples. But if you only care about the rates per sample, you divide it by m, and also if d is fixed, m goes large, the rate is exactly this, right? You give it a rate function. It's average number of bits per sample per vector you assign to your data, right? Give you a very intrinsic measure for the volume of the feature expanding in that space. It's computable for subspace of Gaussian, for mixture of Gaussian, right? Of course, your data could be multiple subspaces, right? Multiple mixture of Gaussian, and fine. If you know the cluster properly, especially in the supervised setting, right? You have samples; they're separated, right? You can compute for each class, fit with the subspace of Gaussian. Right? That's a feature. X is not, right? This is only on Z, right? After the mapping is done. Now, what makes feature a good feature, right? Again, the information gain. Why do we want to separate all the image to 10 classes or 1,000 classes? Because I gain something, right? If I put them as a whole, I have to cover that entire space spanned together, right? To label them. But if I can split them, each one becomes a smaller volume. Hence, the difference between the whole bits, I encode the data, treat them as a whole, minus I code the data separately with k classes. That difference is exactly what we call the rate reduction. The reduction in the rate distortion for the whole to the parts. Okay? I mean, in fact, it's actually measuring how much gain of information I'm getting. That's it. By counting balls, evaluating volumes. Very basic, very universal. Right? And you can see the first term actually says measure the volume of the whole data sets. Right? The second thing is the different classes. It's a compression. So then, if I have freedom to map my data to such a Z representation, which one do we prefer? Right? Obviously, we prefer. You can see that if my data lies on two lines, right? Two subspaces, we cannot prefer the one on the left, right? Remember the neural collapse, right? We wanted the subspace to be orthogonal to each other. Why? From the information gain point of view, you gain the most, right? Because the whole minus parts here, all the blue spheres are the largest on the left. Although intrinsically, the data has the same distribution, lies on two lines of the same length, right? But the information gain, the left one is larger. Hence, if you really wanted to look at the volume here, you want to find the z such that this difference gets maximized. Actually, this is exactly the similar idea, right? People have practiced this contrastive learning. I want my different different data that's kind of different, right? Likely the data points from the different classes gets contrasted, right? They use a very heuristic measure to do that. It turns out using the redistortion, using the information gain, you can measure contrasting data with arbitrary classes, subsets. You can contrast them, you can compress. And hence, this is sort of we try to find a mapping such that the data rate reduction gets maximized. Right? Now, then you try to, then you ask yourself the question, if I wanted the blue balls, right, the whole minus the parts, the largest, right? You say, well, what about I scale the one on the left, right, twice, 3 times? Then the space of blue balls gets larger, right? Then everybody can start to cry and fall, right? Why? The scale is not normalized, right? If you want to compare these two representations fairly, better they are on the same scale, right? That's exactly the notion of normalization, right? So you make sure the feature you got is normalized. That's exactly the notion of normalization. When you compare two representations, the better have the same scale, okay, on the same sphere. Hence, in the neural networks literature, people are doing the batch norm, layer norm, instance norm, group norm. They're exactly doing the same thing. Okay, there's no difference. Just like Zihui says, right? There's a different loss function. They're absolutely mathematically equivalent. Okay, it just matters how you optimize them, right? They make a huge fuss about every paper is about them, right? Just basically, I compare representation across different layers or across different neural networks. They need to be on the same scale. Hence, normalize them every time you are done, right? So once you do this, the question is, if we do this, if I maximize this rate reduction, do I get the kind of desired configuration? Turns out that's the case, right? Just very similar to what Zihui just said, right? Here that he's also each class he assigned one dimension, right? Here each class we actually assign the dimension exactly the same as the class with intrinsic dimension, right? As long as the ambient space is larger than the sum of all the intrinsic dimensions, then you can prove those features gets pushed to orthogonal subspaces. And the rate reduction, if you optimize them, you'll get the right representation. Right? Does this work? Actually, that works pretty well. Right? I mean, you can see that. And the good thing about this, you can see that this is on CIFAR. We can just use let's say we just choose there's the only thing that we can use to learn the mapping, we still use the resident. We'll talk about how to replace that with a white box network just in a second. For now, we just choose neural networks. But the original plus the only difference between these two experiments is that everything is the same training, the same network. But the only thing difference is that one use cross entropy, one use the rate reduction. Right? You can see that per class on CIFAR, each class actually is no longer collapsing. Right? It actually converges about the 10 dimensions, about a dozen dimensions, right? And then the features of each class is absolutely orthogonal to each other. And here, even in converge, right, the cross entropy is still across different classes, still high correlation there. Maybe you train long enough, you get an orthogonal. But this is actually, you can see that this is actually saying that essentially each class is a 10-dimensional subspaces, right? I can compute the principal components. I can plot which image is close to those principal components. You can see that sort out those different classes very nicely. And also, what does this work better? Actually, yes, even on CIFAR turn, right? You can see that in terms. Also, one of the things is that we're not just learning one feature, right? We're actually learning all the features separate apple to oranges. Actually makes, at least empirically, make the process much more robust to label crosses, right? We're using a set of samples to estimate that subspace. Even some are mislabeled, the subspace is still the same, right? Right. So actually you can see that if the 10% all the way to 50% of labels are randomly corrupted, but they still learn very well classifiers, unlike cross entropy. It's affected by that. Right. So of course the remaining question is, for the remaining of time, I'll just quickly, right? So the remaining questions, we're at that time we're a little bit happy, right? This actually reveals what the neural network is trying to do, right? I mean, maybe this is the kind of features. We learn much more diverse features. We sort of explain what maybe each layer, we can evaluate the features, how good they are. But then what's really depressing is that, well, this is still a black box, right? How do you learn this mapping from X to Z? Right? Black box, right? How deep, why is deep necessary? What is doing? How wide, how deep, right? And what is this linear and nonlinear operators doing anyway, right? Why multi-channel convolution? Especially in images, right? We do convolution, but not in the tradition, not in the deep network type, right? The 3D convolution type. Why? Right? None of them is because some of them tried and tested, right? But one good thing about knowing the objective that you couldn't care less, right? If you're clear about the objective, then just achieve that objective, right? I couldn't care less. So remember, our job is to maximize this object function, find a mapping, continuous mapping X to Z to maximize this, right? If I can guess it, I'm the god, right? I couldn't care less. I use deep networks or shallow networks, right? Or guess a kernel to do this. As long as this mapping is mapped. So one thing we think about is that since this is the object function we do, we just optimize. Can we just optimize it? In fact, the recent paper from Hinton precisely said this, right? Nature doesn't do backpropagation, right? If you know the object function, if you know how to value the goodness of your feature, you should do things in a forward fashion. That's exactly what we should do, right? So this looks complicated, log determined and everything, right? Non-convex optimization, but everything we told you guys this earlier is that don't be afraid of nonlinear optimization. If we see a nonlinear optimization, just to do a greedy descent. The least you can do is to do greedy descent, right? Let's just do greedy descent. If you do greedy descent, something magical happens, right, on this quantity. Remember, this is the volume of the whole, this is the parts, right? They're all locally determined. Once you take the gradient of this quantity, something magical happens, right? The first term becomes this. The second term becomes this. The other terms become this. Everybody good at statistics should recognize immediately what they are, right? This is exactly the residual of doing data autoregression, doing ridge regression, using data points to regress each other data points. Okay, nothing else, right? And of course, you can see this is a complicated inverse. Doesn't really matter. Some function, some matrix hitting this feature, right? Hitting the iterate. And this is another matrix hitting the iterate, right? So we write down this delta R. It's actually one matrix multiply the data, another matrix multiply the data. Of course, for each class, apply a different linear transformation, right? It's a piecewise linear transformation on your feature, right? This is, as I said, this can be exactly interpolating as EZ is exactly the residual doing the autoregression of all the data representing. This will show up, right? Autoregression, self-attention, guys, right? They're exactly the same thing. We'll see that immediately. So this is actually just a residual. Depends on the residual. This is very simple, guys, right? I'm trying to compress the data, the whole, right? I want to maximize the first term. I compute the residual. Every point gets represented by other data points. If I want to maximize the volume, what I do, I make the residual larger. If for each class of data, right, I represent each point with other data points. If there's a residual, if I want to compress, I reduce that residual. Very, very basic, right? And turns out that's exactly what the maybe neural network is doing, right? So if the original data is nonlinear, curved, manifolds, then I want to linearize, map to those linearized. I want to compress each class and expand all the classes. I compute a residual. For expansion, I put a positive sign. For compression, I put a negative sign. I reduce the residual. That's it. Right? Each layer is just doing that. And of course, here is one thing where the nonlinearity shows up, because for each class data, I need to know which class it belongs to. Which class that particular data feature point needs to compress to against which class, right? Then since if I don't know that class, I just do a soft class. I just do the soft mass. Assign that to each class. Hence, you get this. So this actually exactly applying the feature to the corresponding class, right? Doing a soft class. You get it actually the softmax. By the way, one way to approximate these things is exactly using Redu. I mean, I'll skip that. So we're all engineers, right? If you write down the optimal function, unroll the optimization algorithm, then of course we can do diagrams, right? From the previous iteration to the next iteration. You get a diagram, this feature gets hit those linear transformations. By the way, this is doing the gradient descent. There's the residual part. This goes through the nonlinear soft mask, doing the normalization, and go to the next layer. Nothing else. So everything here is completely derived from scratch, from the data itself. Right? And we call it the Red network. So everyone, does this recognize this looks like? Right? This is exactly the residual network looks like. In fact, later on, people find the res next works better than residual network, right? Parallel channels. That's exactly the parallel channels. In fact, in the transformers, why there are multiple heads? Because for different classes, different substructures, you need to assign them properly. The data goes to different channels, right? Gets processed differently, and you need to have parallel channels. They're actually just doing optimization, doing compression correspondingly, right? So, but very different from all this architecture, right? It gets trusted. You need to randomly initialize carefully, and you do backward-looking training. Everything here is completely computed from the data itself, forward fashion. No training whatsoever. Right? Just like a PCA network. And look at even this transformer, right? Has exactly the same mixture of experts. Transformers has this Google's one training has exactly the same meta structures. They're all trying to emulating the same thing. Right? Does this work? Actually, it does, right? So actually, in the purely forward constructed networks, actually my students have some fun, right? They actually construct Tosan layers. If you want the deep layer networks, of course, just like a running deep neural net, just running optimization algorithm, right? You can do the iteration forever if you want, right? If you don't care about computing, but that's the wrong thing to do, right? It's not efficient. But you actually can think as also for group invariance, you can actually try and train this. So this is actually just for grouping data already have subspace structures. What about Sam also talked about many more problems, right? We actually have data, maybe want to group all the transform cluster, right? Samples all as a one classes. Don't worry. I mean, one do just treat all the transform sample as one class and push them into one subspaces, right? Map them into one subspaces. What about we compress all the translated or transformed sample together? What will happen? Shift transformation, right? Let's consider shift transformation. If you compress all the data, think about a one-dimensional signal where I shifted one by one, right? Do a rotation translation and rotated, cyclic translation. I compress all the data together into one subspace. What will happen, right? Computed rate distortion, remember, right? Everybody can become a cyclic matrix. If this is the measure, right? Turns out the E channel or C channel, if you compress all this translated signal together, you automatically, the E channel, C channel, the operator acting on the feature becomes a convolution. They actually become multi-channel convolution. Precisely the structure of the modern deep neural network, right? Even with crosstalks, I'll skip this for the interest of time, right? The E channel, C channel actually precisely become cross. That's just a matter of actually they become automatically multi-channel convolutions, right? And it turns out very interesting, right? This E channel, C channel turns out they need to take a inverse of a Hobsbawm matrix. Turns out this matrix has block diagonal structures. It's much more efficient to compute in the frequency domain, not in the original space-time domain. Okay? Don't forget our brain computing in frequency. Right? This is at least one piece of mathematically, proof, right? Evidence, right? Computing in frequency domain is much more efficient, right? Computing in time domain is the n to the cubic, but in the frequency domain is linear in the number of pixels. Probably nature already figured out. It's much more efficient to do translational invariance in the frequency domain. And now you actually can derive, right, the whole neural network. Write down the neural network, every operator, every parameter in a pure white box, right? And in frequency domain. And so this turns out this just gives us a little bit of a very interesting way, right? You have multi-class signals, you lift it to multiple channels, do a sparse coding. I'll skip that. But then what really the neural network is trying to do is try to do a map different classes, compress each classes into subspaces and separate them. And everything. You don't decide anything here. As long as the object function, your object function is maximize the information gain. Human, you don't get choose almost nothing. Right? You just try to gain that. Maximize the information gain. Every part. Linear, nonlinear, normalization, everything gets expanded. Right? Actually works pretty well. You can see. And by the way, nobody is stopping you from fine-tuning this. Okay, just like we have the algorithm to solve sparse representation, right? Remember the Lista algorithm, right? Yang-LeCun test. Oh, I can, if those iteration, each iteration is not effective enough, I can fine-tune those parameters. Nobody can stop you from doing that. That's exactly what backpropagation is doing, right? If the output is not good enough, I backpropagate error. I can fine-tune the parameter. I get a higher text accuracy, right? If the number of iterations is fixed, I can make each iteration more effective if I have enough training data. That's exactly backward. But that's not a natural way, okay? Nature never do that. Nature cannot do that, right? We cannot do things end to end, okay? Well, on Thursday, I'll introduce another thing. Actually, that's exactly what the Quinton's latest paper was talking about, right? Nature correct error not through backpropagation, through loops, feedback loops. We'll talk about it. So this is actually to try to conclude a little bit for the interest of time, right? So basically, we saw a few examples, right? If I have data, I want to cluster them. You have to tell me why you gain. Why do you do that? The only measure is that it's compression. Because I separate, I gain information. Okay? There's a very fundamental basic measure there, right? Bin counting, counting balls, packing spheres, right? And it actually works in both classification. But this works, the difficult part, guys, if you put expression R there, you better know how to evaluate it. You can compute it. The only case we know how to evaluate it efficiently are the Gaussians or subspaces, not arbitrary distributions. Stop talking about those quantities that you cannot compute for arbitrary distributions, okay? Yes, admit if you are approximating them, you're sampling them, right? But don't claim you have a better solution. Well, I'll talk about on Thursday, especially about GAN, right? About learning the generative model. That's even more worse, the situation, right? So, and now the question is, then maybe we can make, if the Gaussian or subspace are the standard structure we want to learn, then we want to learn mapping to make the data that way, right? The natural distribution might be very complicated, but we make them linear, make them separated. Right? That's exactly the role of neural network. Try to achieve this in an incremental, iterative fashion. Right? And of course, the rest of the job is just how to find the right optimization strategy to do it. Right? That's still open, by the way. Right? So basically, deep networks just try to do this. Right? The object function of neural learning, any learning, I argue, is try to gain information. Any part of our brain is actually trying to gain information. A principal approach to interpret the deep network is just optimization. Could be gradient descent, could be a power iteration. We'll find out. Right? So once you do realize this turns it's about the 70 years, right, since the inception of deep networks, 1940s, right? For 70 years, the practice of deep network has always been on the left column, right? We fit input-output labels. We fit input-output. Right? And the architecture, we try and error. We try, test it, right? The convergent, we'll see. Layers operation empirically. Well, what they do, softmax, ReNU, you try. Which one works better, right? For shifting variance, we do CM plus some augmentation, but we cannot guarantee anything. The university has to carefully randomly, or pre-trained. And we do backpropagation. Even after we did the backpropagation, the network still black box. Well, you can argue it's a gray box, but still, you don't know quite, right? But the worst thing, right? Google, Facebook pays $1 billion to train those big models. Actually, they call the representation latent or hidden, right? That's very depressing, right? If I pay something for $1 billion, it's hidden to me, right? Now everything is turning upside down now, right? So if you have a more principled way of looking at it, if you know maybe the network is actually trying to gain the information, if the object function is clear, what I want to optimize is clear, everything becomes clear, right? Then maybe I'm just to optimize that objective. The network is precisely trying to achieve that, right? And each layer is just do gradient descent, or maybe more effective operation. We can find out later. And then you can just do this, we compress all the invariants together, and get the invariant, the structure will pop up. And the network is actually far more computed, right? It's very natural. And of course, you can do forward, backward, fine tuning. Nobody can stop you from doing that if you have a 5,000 GPUs, right? A lot of input of data. And the point is that you actually end up with a white box architecture. You know what each layer is doing. And also, the most importantly, after you're done, right, you know this is what you're getting. The features are linear, become structured, compact. And we'll see on Thursday, we can go back, right? How do we make sure what we learned, that structure is exactly correct? So there's actually a lot of things, right? So of course, today I talk about the case you already know different classes, the samples for different classes are already labeled, right? What if you don't know that? Some of the students here are already working on that, right? How do you jointly optimize the representation and the clustering if I don't know the label? Again, but the principle never changed, right? Having the label, without the label, is just different variable in this object function, right? With the correct label, this difference gets maximized. That's it. It's the same quantity. Remember, we're doing the clustering. I can do pairwise, for God's sake, right? Merging them. I only compress what's similar and separate what's dissimilar. That's all this object function is doing, right? And once you realize the network layer by layer is doing optimizing this object function, 300 years of studying optimization helps you to find a better optimization algorithm, design architecture, right? Here, the Redoux network is just doing the gradient descent, which is the simplest, most naive gradient descent, right? You can do much better with accelerated gradient descent, other structure in your operator, right? Most importantly, remember this gradient of the rate distortion, right? Looks like this, right? Who says this is the only way to approximate it? Who says I have to approximate this inverse with the E matrix? Do von Neumann expansion, right? You can do the von Neumann expansion of the inverse. What do you get? Keep the first few term. Expanding this, take this. This is exactly the terms that you saw in self-attention transformer. Nothing more, nothing less. Okay? The first order approximation of that. Right? So you can see that. Remember, guys, right? When neural network come out, everything is very mysterious, right? Or resident trial error. I mean, there's something. Of course, the theory fall back. People cannot explain. People think there's something very mysterious. Hence, for long years, many years, there was all this work about the AutoLAS, AutoML. We do random search. We search all the different architecture. We believe there's something magical out there, right? But after how many years now? Only two networks sort of survived. ResNet, Transformer, right? They're exactly approximating the gradient of the compression or expansion. This is the only thing you can compute. By the way, the score matching function behind this so popular diffusion model are exactly computing the same quantity. Okay? The gradient of how data volume change. Nothing more, nothing less. This is the only thing you can compute reliably, accurately in high-dimensional spaces up to first order. Okay? You can approximate more accurately, nothing more, nothing less. Everybody is doing the same thing. Right? So that actually turns out that this is actually another interesting thing, right? Through this approach, you actually can see not only this is a sort of engineering information theoretical driven, but actually start to see a lot of things you derive from, deduce from this approach, resemble a lot of things that people already observed in nature, right? The sparse coding, spectral computing, subspace embedding, and we'll talk about on Thursday, the feedback loops to ensure, right? That is exactly what we saw in nature, in the primate's brain. Right? Those mechanisms that precisely, as I said, maybe our brain or memory is precisely trying to gain information. And that measure is very basic, very computable, very tractable. Right? And we'll see that. Today we talk about how to learn this mapping X and Y, what is the object function of delta Y, but how can we guarantee? Remember, guys, the optimal solution may not be the correct solution, right? Very huge difference. Okay, optimal solution may not be the correct solution. Do you get it? Right. If you still think these two are the same, check your mathematics. Right. So how can you make sure I optimize this thing? I get some z that's actually precisely the correct for the x. I'm not. If the oranges are 5 dimension manifold, how can I make sure the z is also 5 dimension, not a 6, not a 4, not overfitting, underfitting? How can you guarantee that? How can you guarantee your solution is consistent, is correct? So we have to be able to go back. How do we do that? How nature does it? Of course, you can say, oh, well, let's do backpropagation, right? Have a lot of billions of pairs. That's what exactly they train all this chat box, right? Reinforced learning, if I have lots of pairs between x and z, label data, fine, do that. Nature never do this. Nature cannot do this, right? Cannot afford to do this. Then what they do? How can they still learn solution probably much more elegantly, much more efficiently than what we do now? Right? So what are the larger mechanisms? We'll talk about on Thursday, right? So how do we go back, close this loop? Right? So anyway, that's sort of conclude. And also we'll start to see this one framework actually works in all settings. Start to supervised, incremental, unsupervised. And all approaching the state of art. Things gets much easier and better. So this is the main reference for today is actually this paper. As I said, it's the GMR paper. It's really about this one direction, right? How do we build deep networks in a white box from forward fashion? But that's give you the optimal solution, likely, but not the necessarily correct solution. So we need some additional thing to make sure it's correct. Again, as John mentioned earlier, right, this whole tutorial based on some of the mathematics based on the high-dimensional data analysis, statistics, and geometry. Right, this book gave you some of the introductory material, but many of the things we can talk about today, or maybe on Thursday, we'll talk about some latest development in this direction, following this direction. Yeah, that's all. Thanks. Sorry, take a few more minutes. Couple quick questions, and we can go through. Yeah, some of you can ask questions. If there's some question online, I'll answer first. Some of you guys, I can maybe take a couple of light questions, and we can, chat over the coffee. Okay, anyone? Any question? Yeah, we're running a little bit late down for a coffee. Quick question.
If apples are aligned in 2 axes, like red apple and green apple, and we have a label of only apples, and we align them in the simple space in one plane. So that would be wrong in some sense, right?
No, so here's quick question for your question is that even each class may have a substructure within the subspace itself. Okay, if it's sort of uniform distributed, and the object function will push them into more like a Gaussian within that subspaces, and the different characteristic attributes. In the Thursday, you'll talk about. I'll show you more example. Different attributes may shows up at different principal components. So maybe green apple, the different color may become different principal component. Color becomes one principal component. Shape becomes another one, or different characteristics. Or the side apple, upside, top view, side view apple will shows up different principal components. So there's a finer structure within each subspace. But this is just a push different classes into one subspace, including potentially even the rotation, the transformations. You can even imagine, right, in the subspace, if you group all the apples, including the rotated render, so even the rotation will embed it in somewhere as a curve in that subspace. So similar to what Sam has, right, discovered. But that transformation will not be one-dimensional, right, because all the poles could be multiple-dimensional, but they will be embedded into that subspaces. Yeah. So that's what you want. The question, of course, what exactly they are, how can you further disentangle them, and then how do you sample them, right? The whole point is that we want, see, this is the point. We want our representation Z, whatever distribution in that hidden space, is not hidden, for God's sake, right? That's why the GAN or after diffusion model, you still have to sample it. You have to guide where to sample, right? You cannot arbitrarily sample and generate something that will generate mostly gibberish, right? So this is the question: is that we want our structure Z map different classes in just like in our brain. We imagine an apple, we see an apple, right? We don't. It's not a randomly sample. Then we diffuse the model to try to draw sample. That's not going to work, right? Our memory has to be highly organized, highly compact. We know exactly which part of. Actually, that's how some of the scientific experiments showing, like monkeys' brains, they actually organize different classes of objects precisely in different regions of the brain. Right? They're highly like there's one region just encode all faces, human faces, right? Just a few hundred neurons. That's it. Encode all the faces as bases, coordinates, right? Representing all the faces that the monkey has seen in his whole life, right? So it's highly compact, highly organized. We want to understand what that process is, right? Hopefully, likely the whole neural network where layers are precisely doing that to maximize that information gain based on the separability and the compress of each class. Right. Good. Yeah, we can probably move on to. Oh, you have yeah.
Sorry. Just one last question. This is probably dumb, but you talked about supervised and unsupervised for classification tasks. Mm-hmm. Does this information gain also extend to regression tasks, or
to which task?
Kind of a regression task instead of like a classification task?
So in fact, you can think about this object function is already doing implicit regression, right? You can see just like PCA. PCA doesn't, PCA just find a correlation among all the variables, right? You can think about it's doing joint regression. Of course, it doesn't specify which variable you regress against other variables. It's finding all the correlations, right? Then depends on future tasks. Once you find that subspace, then in the future you can find out which features are predicting which labels. You have a new variable, so you can decide which those subspace variables predict that variable is best, right? So you can think about this. In fact, the whole process, even using labels, we're learning the structure of the data, not the task. It's actually pre-trained, right? We try to build a memory based on what's similar, what's dissimilar. Very opposite almost to the information bottleneck. It's trying to distract, give me a label set, right? Label the data. I try to find from the data which one maximize the correlation to the label, as if the label is ground truth. That's why you learn the label. You learn the neural claps. Everything converts to that label. Here's completely opposite. You pay attention to X. I want to learn a Z, which is a mirrored image of X, but organize the image, right? Beautify the image of the data and make sure it's consistent. It contains everything predictable about the data, right? Compress it, and then the neural network just play the role to optimize the measure, your beauty measure. Of course, this principle is not limited to subspace, right? Subspace is the case we can evaluate efficiently, Gaussian, in the Z case. Of course, for other class of data, other distribution, if you know the rate distortion, you can measure the distribution very well. The same principle applies, right? You have a measure of information gain. The only thing we use subspace is because we know how to, the log determinant are the closed form for measure that log, the rate distortion. For any other distribution, Laplacian or whatever, good distribution you like to, maybe genetic data has a different binary discrete distribution. The same principle applies. Right? In fact, the information gain originally was used for discrete variables, not for continuous. But it turns out it's easily generalizable if you use the rate distortion to generalize it. Right? But the principle stays. It's the same. I believe it's very universal.
Yeah. Thank you.
So what if you actually use some of those discrete optimization techniques instead? Would you get new networks?
No, well, there's some still didn't remember. I think I mentioned briefly. We didn't get time. Do you have a poster? Do you? Yeah, about the clustering, right? Yes. So we didn't today. We didn't talk about how to optimize the pi, right? Right. See, for example, pi depends on how do you. Pi is actually the clustering, right? Which point belongs to which group? You can, of course, you can approximate it. Parameterize with the membership, right? With a continuous variable to optimize to do gradient descent. I don't know. I mean, we never do this. What is the architecture you get from there? You can do that. You still can do the gradient descent against the continuous membership, right? You get some operator, but of course you can depends on how you parameterize pi. If it's a discrete variable, then you have a compilatory optimization. That's actually something we got stuck when we do clustering, remember. The clustering, you don't know how many partitions. We actually do merging. We do pairwise merging. In clustering, you can still do that. I think, until some of the students already try. Renee's have tried this as well. But regardless, you have this thing as a measure. The correct pi and z give you the best delta R. If you are God, you can guess it, right? You don't care what the network is. Network is just the means to the end. Whatever you can get that optimal solution for your data, you're done. Right? You learned the best you can, right? You get the best memory. Your brain already memorized the structure and the samples perfectly, right? So that's the common game there. Now, the rest is just the optimization strategy to me. Also, the starting point is different. If I know the pi or some initial z, the optimization gets easier. If I don't know the pi, I just have to find it. Which one is the best? The optimization becomes harder. Right? And because of that, I'm pretty sure in the future, in unsupervised learning cases, maybe there's a different architecture, right, than the ones works in a supervised setting. ResNet transformer, they are sort of customized to the supervised setting. We don't know, to take into account the unsupervised clustering together, what additional structure, what additional operator should be there.